Hello there. Thought I would put all of the 4 types of centers of a circle that we've talked about together in one picture to see how they can kind of relate to each other. So you'll see I have my triangle ABC, and this point, the circumcenter, that is outside of the triangle. Sometimes it can be inside the triangle, and that is a point that is equidistant from the 3 original points. The incenter must be inside of the triangle. That's the point of concurrency of the angle bisectors, and it is equidistant from the sides of the triangle. And then we have a centroid, which is a center of mass for the medians, and the orthocenter, kind of less talked about, but that's a point of concurrency for the altitudes of the triangle. So I'm going to sketch these a little bit, get a bit of a visual. Try to use different colors. It'll wind up overlapping quite a bit. So there is one of the perpendicular bisectors, and now we'll try to get it for the other sides too. There's another one, and on the other side, that one was much harder to sketch in, but those are the perpendicular bisectors, and they are equidistant from the endpoints there. Those are all the same. Now the incenter is created by angle bisectors. There's the first one. This will be not the prettiest drawing. You'll have to do some of this on your own. On the other side, you got that one. Should weave through it. Alright, and there's the top one. And this creates a point that is equidistant from the sides of the circle, or the triangle. You can create a little inscribed circle in there. And then we have the centroid, and that's created with medians, which connect to midpoints. So notice I'm drawing the purple line out to where that perpendicular bisector was for the first one. It's got to go there. It's got to go to the midpoint. There's the second one, also goes to a midpoint. And the third one also goes to a midpoint on another side. Wow, this is getting pretty ugly there. Now the centroid, there's not a circle that we're going to create out of it. But it does work as a center of mass and have other interesting properties too. Okay, the last one that I'm going to talk about, simply because it's another point of concurrency, is the orthocenter. And just like the circumcenter, this one can wind up outside of the triangle. And it is created by dropping altitudes for them. So the altitude from B to its opposing side here, that extends well out past that line there. And when I start doing the other altitudes, there's actually no place for me to position a line from C along the segment AB that creates the 90-degree angle. To create their 90-degree angle, I have to go outside of the shape here. And I get the 90-degree angle out here. So this segment here would be, if I rotated all of this, treated this as the base, that is the apex, this segment here would be the height that I would use to calculate in like the area of the triangle if it were rotated some way. So I see that they intersect out there. And then the last one to do is the altitude coming from A that'll intersect along the extended line BC. So it's not going to intersect on the segment BC. To get that 90-degree angle, I have to go outside of the shape. There it is right up there. And that's their point of concurrency, the orthocenter. Now, we went over in class why the perpendicular bisectors are concurrent and all intersect at a single point. We proved that. We also did the same thing for angle bisectors, being at the incenter. The proof for why the medians are concurrent is more advanced, but there's going to be a part of a proof that can lead you in the direction for how you could go about doing that. The orthocenter proof is not as involved as the centroid proof, but it can be quite long if you want to prove it rigorously. But there's a neat observation on how the orthocenter is actually related to one of the other centers. And I'll let you discover that one also in the packet. Okay. Thanks for watching. Character and Scholarship for Life.